Alright, not a question of scale this time. A question of simplification. GCSE level physics. Completely immovable solid surface, which I've just marked with hatches to make into a mirror. Ball falls onto it, hits it at that angle, bounces, departs at that angle. That's a right angle, and that angle, and that angle will be equal because boing, because that's how it happens. If you desimplify that from point hitting brick, you get a very slightly more complicated model, not at the point of impact, but after impact, at the bottom of the ball's travel. You have the inner and outer sides surfaces of the ball, because the ball's skin has thickness, on a surface which slightly, if it's this stuff, yeah, this is plywood, it bends, possibly distorted by the impact, because the ball's weight is pushing it down, but also the ball is being bounced, therefore there is a force pushing it upwards. That's nothing like all of it. This part of the ball is being pushed upwards relative to this part, so you have up there, down there, shear stress around the part of the ball that is in contact with the ground, just in general. You also have this part of, I should switch actually, use red. The outer part of the ball is under compression. The inner part of the ball is under tension, because it's being flexed that way. If you extend the drawing of the ball all the way out to the outside, it's all outside, all the way out to the horizontal circumference of it, because it's being flattened there and it's got air in it, you have an increase in air pressure pressing against it all the way around, and it will be pushed outwards here, so this part will be under tension on the outside and under compression on the inside. And if you did this with a ball that was slowly coming apart from old age, you would start to see cracks and splits appearing in it, and it could indeed, if it was an eggshell, shatter all the way around there as the middle bit was pushed up. So dot bouncing off a line just ain't in it. If we talk about this part flexing, you will also have compression there, shear stress there, and tension down here, as that bends. And that's before you get into air resistance. That's just being converted to heat. What's this got to do with anything anything apart from a ping pong ball bouncing off a wall? Let's jump to another one. I don't have the exact quote on the screen to read out to you, but there's a NASA document that somebody found, which is about time to climb, and it treats the aircraft as a point mass flying above a flat planet. I went, oh my god, look, NASA acknowledges the Earth is flat. Bullshit. They're treating a plane as a point mass, for God's sake. Does nobody notice that? This is actually, again, a simplified description of a simplified description. People who are fans of XKCD will probably be familiar with the infinite plane of uniform density. It stretches to infinity that way, and that way, and that way, and that way, and it is exactly the same density all over, which means wherever you are, gravity has the exact How far you are above it probably does matter, but apart from that, wherever you are above it, gravity has the exact same strength in the exact same direction. Those of you who know that gravity ain't the same all over the Earth know this is already not accurate. Also, curvature. Oh god, that's going to start such a shitstorm in the comments. In terms of this point mass aircraft, you have, what can I use? I can use green, which might be visibly different, might not. Thrust. As the aircraft is moving through the air, its wings are generating lift. As it's moving, there is drag in the opposite direction of its movement, and of course it has weight. Because of... No, I'm not going to insert a desert file here, but because of gravity. Now, that's going around in a rectangle. The reason I've drawn it that way, rather than what you might think is the more obvious drawing, if you just want to discuss what forces are on it, it might be more intuitive to draw it like that. Thrust, drag, lift, weight. But if you draw them this way, that is vector addition. The magnitude of the thrust, or the weight, whatever, and its direction is a vector, and they add together exactly like that, and the net force on that is bugger all. So it's not going to accelerate, it's going to continue in a straight line at uniform velocity. Newton's first law of thermodynamics. Cruise, baby. Or sit still. And I can draw multiple aircraft in these stable states. There's a little point mass aircraft there. Rather different aircraft. It's got its nose up, it's generating a heck of a lot of thrust. Lift is in at a right angle to the direction in which it's thrusting because of the way its wings are mounted on its body. Drag is back along the direction of travel, and weight is of course straight down. That's an aircraft that is travelling that way, probably very fast, high thrust relative to its weight. It's fine. And another one, which is going to be in kind of the inverse of this engine screaming like mad climbing situation. This one has got its nose down and barely any thrust at all. Throttle almost closed. Because its nose is down, its wings are lifting not only up but slightly forwards at right angles to where it's pointing, generating a lot of lift. And it is travelling downwards, so its drag is backwards in the direction of travel, and again weight straight down. Alright, to have that much drag, if it's the same aircraft, it's got to be going bloody fast compared to this one. This one's just puttering along. Sopwith Camel, fighter jet climbing, Cessna on a glide. This is as close as a powered aircraft gets to gliding, pretty much. Without shutting off the engine altogether. Almost no thrust down, lift that way, keeping it going forwards through the air as it descends, drag backwards and up, and its weight pulling it down. And these are all stable situations. And if you make a change to one of these, you can, for example, have a little chap in a Cessna ease back on the stick. There's a little point mass of a Cessna, points its nose higher without changing anything else. Thrust is going that way. That is a very steep climb angle for a Cessna. That means his lift is coming back here now, and assuming he is going upwards, his drag is going to go back to there, and weight is down there. As you can see, if that dot's big enough to see, there is now a non-zero vector sum. In other words, those 4 arrows put together don't come back round to where they started. That's a force in that direction. So this thing is going to be accelerating in that direction. Nose is pointing that way. So it is slowing down and it is climbing less and less rapidly. That is going to move this drag vector to somewhere more like there. Because it will be slower, so it'll be shorter, and it won't be climbing as much. Hang on. It won't be climbing as quickly, but it'll be slowing down a lot. So yeah, somewhere like that. And the new weight vector will be down here, and it's still going to be slowing down. If it slows down too much, it stalls and falls out of the sky. With the guy doing the glide, well, he's going to glide down and he's going to land, so forget him. The guy in the fast jet doing the climbing, if we leave him alone in not only above an infinite plane of uniform density, but in air of uniform temperature and density, he's just going to carry on. But if he keeps climbing and climbing and climbing in air that decreases in density with altitude, a lot of things are going to change. For a start, his engines have less thrust because there's less air for them. The air is less dense, so he's getting less lift. and he's getting less drag. Also, because he's further away from the centre of gravity of the Earth, he has very, very slightly less gravity, but you wouldn't notice. On here, what we've got, it won't necessarily be straight down, but we have got this straight down vector sun. So he's not going to keep climbing at that rate. At some point, trying to climb like that, he'll not be climbing anymore, he'll just be flying level with his nose up, very slowly. Or he'll stall and fall out of the sky. But all of this is point masses. Treating the aircraft as a point mass is ignoring a lot of things. Hundreds of them are the fact that the aircraft isn't a point. Take our little skylane job. You have got the windows where you sit. This isn't necessarily an accurate drawing of a Cessna skylane, but what the hell. You've got a body something like that shape. Folded undercarriage, very neatly stowed away so you can't see it. It's important. You have got the wings up here. And I've given them a blunt back end for a reason, don't panic. You've got your tailplane, or your horizontal stabiliser, whatever you want to call it, back here. And you've got a fin, out of which I have left a notch, for a good reason. Wing tip. Let me draw in a wing tip just there. Sticking off the back of it, back of various parts of it, you have got flaps, ailerons, elevators, and rudder. And sticking off the front, you've got an engine. No, sat in front you've got an engine, sticking off the front you have the propeller. It's kind of the it's like the Volkswagen Beetle, sorry, Volkswagen, get the accent right, Beetle of the aviation world. It works. So it's treated as the centre of lift is going to be somewhere pretty much central to the wings, so up there, and the centre of gravity had better be somewhere pretty much central underneath them, so down there. And it's not hard to figure out the centre of thrust is the centre of the propeller. Actually, a little Cessna skylane that's generating half a G of thrust is doing bloody well. And drag, well, drag is ultimately going to have to be back from that, in line with thrust. But when you want to tip this thing's nose up, you don't just magically rotate a point mass. What you do is move this red bit here down to, up to there. You have airflow over this thing. Could do with more colours to illustrate airflow, but I'll use green. What was airflow straight past it is now getting deflected upwards because that's at that angle. That creates a downward force there around this centre. I haven't really drawn that circle around the centre, but that is going to push the tail down, which will cause the aircraft to point upwards. But you're changing a whole lot of other things. You're changing the airflow around the wing that's generating lift. Because now, once the plane is pointing upwards, but still it's pointing that way but travelling that way, the air is hitting the wing at a different angle, which gives the wing more lift but also more air resistance, which is going to slow you down. It's taking energy to do all of this. So this whole model of the aircraft flying through the air, it is not a point mass. Among the dozens of other things wrong treating as a point mass, you have, I've switched from using red for forces in the ping pong ball to using green for forces here, don't worry about it. You've actually got tension pulling apart the top there and squeezing the bottom here. You've got shear stress in the tails, it tries to snap that off. You've got tension in the bolts, you've got shear stresses in the bolts, you've got all kinds of other forces acting on this thing. And once it's climbing, drag isn't necessarily going to be in line with the thrust. Because you're climbing at a different speed, you've got different airflow, you've got if the lift from the wing isn't exactly straight up, if it's a tall backwards, there's a component of drag there, which becomes a backwards force there, tilting the plane upwards, corrected by this thing. So you end up having more drag back here and more downward deflection of the air, up thrust here to balance it. You've got loads of forces that aren't accounted for by this point mass in this NASA document that people love quoting. So with your aircraft flying, already it's a heck of a lot more complicated. Yes, this is part of my previous thing. Sun, orbit of Earth, orbit of Mars. Actual size of Sun scale. The solar system is mostly empty space, so I've got plenty of space to draw on it. The other thing that changes, there are thousands of them. Anyone who's watched a cloud, like out of a plane window on the way past, may have noticed they change shape. They kind of look like mushroom clouds in slow motion. Something similar going on. If you boil a kettle on a really cold day outside and watch the steam cloud form up, it does the same thing. It's going up in the middle, it's coming down the sides. Even if you can't see a cloud, there's turbulence. So with your aircraft, which I just threw away, drawn from a different angle, as you're travelling through the air, different bits of this plane are going to be in different parts of the air. So you might have more lift there than there. You might have an up thrust there and a down thrust there. You might have both of these problems at the same time. They're not really big problems. If you have, you've got torsion forces in the centre and you've got a net force trying to roll your aircraft to the right. You could also have wind blowing your tail fin this way, which you can correct using the rudder, which just deflects the airflow this way, pushes the tail back. These are forces for which the pilot or the autopilot has to compensate. So the whole time you are flying, you're making tiny adjustments, or potentially very big adjustments, to your aircraft just to keep it going where you want it to go. And I don't have the appropriate tool to illustrate the next thing. But you're flying through the air. Let's remove that. You have a map of a completely fictional country. You are taking off from that runway and you want to land at that runway. And you've got convenient rivers along the way, and small ones there and here. I'm not about to design an entire Lord of the Rings world for you, but you have landmarks. So you take off, and if it's a completely still day, you take off from here, you turn that way, you fly a straight line to there, you turn that way, and you land. And that's easy. If it's not a still day, there's wind. Was that going to sound condescending or conspiratorial? It's hard to be sure when you're saying something that obvious. There's wind. Wind could be, for example, that way at that speed. You're flying through it. You're not flying over, well, you are flying over the ground, but the aircraft gives no fucks about the ground unless you get really close to it or hit it. The ground does affect the wind. If you fly near a mountain range, the wind hitting the range is deflected upwards and then it goes back down again. You get this wave behind the mountains. Somewhat exaggerated hillsides, airflow over them. you can actually get this wave effect up here, way up into the air, high above the hills, and that affects aircraft flying up there. And it's at a slope, and you get less wind here than here. You get a lot of wind there, and very little wind down here, and you get rain, clouds forming and rain, which changes temperatures and density. As it goes up, the pressure drops, therefore it gets cold, therefore the clouds water condenses out of it and rains, and then you get dry air instead of humid air, and that affects airflows. So it's this big complicated mess. Right, how to plan this on your map with the aid of a ruler. You can mark on your map that you want to fly that route along the ground, and you know you are starting from there. You also know how fast you go, and it would be nice to have a compass so I could draw accurate circles at this scale. So you know you can go somewhere on that circle. You don't know where to point yourself. You know which way you want to go, you know how fast you're going through the air, and you know that the wind on your journey is that strong in that direction. I shall draw some vaguely similar arrows. And vaguely similar is an actual significant point. You know, in the time it takes you to fly that distance through the air, the wind is going to move, the air mass through which you're flying is going to move that far over the land. So you mark the wind on your little clear piece of plastic, and you mark, and it has circles, and you choose a circle for the speed at which you're going to be flying, and then you drag the centre until the circle for the speed at which you're going to be flying goes through the start of the leg you want to fly, and the wind vector is exactly on the line you want, the ground track you want to follow, and then you fly the bearing from start to where the centre was when that happened, and your actual speed along the ground will be the distance from the start to the sum of those two vectors. It's another vector triangle, which is how you add vectors together. So as you take off on this map, you don't point yourself that way and fly there. If the wind is blowing that way, you have to point this way and fly diagonally because the air is moving. Or, if it helps, think of it as the land moving that way relative to the air until you get here. And as you cross this river, because you've planned this route, you know you should pass that junction of rivers at a particular time. If you find that you get to these rivers and you're actually there, you need to change course, which, if you're flying a passenger aircraft, you will do as smoothly as you can so that nobody ever knows you made a mistake. Again, lots of tiny adjustments being made along the way. The wind won't be the same the whole distance, it'll change as you go. And the other change, this is a drawing of a cross-section through a really small planet, or it's a normal-sized planet, just scaled way the heck down. I don't know quite how big that radius would be, but you'll be flying at an incredibly low, there, to your aircraft. If your aircraft is flying above that, it's been suggested that if you set off from what is currently level, from that point, you should end up out in space. As already mentioned, you're always making adjustments anyway, and the higher you go, the less lift you get, so you'll start to drop. As you won't start to drop, you'll cease to go exactly forwards and start going slightly downwards as well, and the airflow hitting your horizontal stabiliser will just lift it and keep you going nose first. Even with ridiculously simple point mass, if you do go in a straight line out there somehow, the forces, I'm switching back to red forces, you would still have thrust that way, you would still have, assuming you don't run out of air, you would still have lift that way, and still have air resistance that way, but centre of that circle is somewhere down there, weight would be that direction. There would be a net force pulling you back, slowing you down. The slower you go, the less lift you generate. If you have less lift, you're going to be in that situation. So you can't just leave a plane climbing and expect it to keep doing it, because it will actually slow down and generate less lift and cease to climb as fast and tilt. And in amongst all the tiny adjustments you make, you'll be accounting for that anyway. So when we talk about level flight, we do not mean that straight line. If that black line is sea level, then this dotted line, I have not made measurements here, but this dotted line could, for example, be flight level 200. 20,000 feet above sea level. Space. Not flat, constant distance above sea level. See, as this change is happening, your aircraft will cease to fly in a straight line.